The following presentation is in fulfillment of the requirements for EUN632 Digital Fluencies for STEM, Task 2, Teaching Reflection. Hello, my name is Sonia Stitt. I currently teach in an Education Queensland independent public school in Brisbane. I cover various roles including classroom teacher, STEM coach and digital technologies teacher. I'm also a Queensland Tech Schools Ambassador, I co-run our Lunchtime Code Club, and I'm responsible for our technology newsletter. The following STEM activities focused around the digital technologies curriculum and was executed during a Year 3 digital technology lesson. It has been replicated in a Year 5 classroom and in Code Club. Students worked in groups to collaboratively use visual coding to move a sphere from one end of a maze to the other and back again. The learning goals were to fulfil the requirements of the Australian Curriculum of Digital Technologies. The achievement standards covered centre on algorithm design and data. Students worked collaboratively to develop their algorithm to work towards a solution, which is an integral 21st century skill. The STEM education practice, or the Sphero Maze activity, was engaging for students and it required and reinforced several digital fluencies. Students' level of fluency affected their confidence to attempt the task and their ability to complete it. It was essential that students already have an understanding of visual coding. Students were exposed to this through direct teacher-led teaching of Scratch programming. Students were exposed to the problem-solving skills of computational thinking during a previous Scratch unit, which is a vital digital fluency. Students also required a level of skill with using a touch screen and an iPad, such as using click and drag and navigating between tabs. This allowed students to navigate the Sphero EDU program with a greater degree of speed and accuracy. Students benefited greatly from having a growth mindset when debugging the algorithm. Students were required to work in small groups, which led to the need of having collaboration skills and communication fluency. If students could not master working in a small group, their completion of the task was hindered. Finally, the need for digital confidence when using a peripheral device and maintaining connection to hardware was also integral to the accurate completion of the Sphero Maze activity was extremely engaging for students of multiple ages and reinforced their knowledge of visual programming and their digital fluency skills. It was relevant to a primary school context. No temporal constraints were observed, although it should be noted that providing a context and background information for the task removes spatial constraints that were present. In this context, the Sphero Maze activity promotes independence as it relies on students' previously gained knowledge of Scratch in order for them to be capable visual programmers. It embodies many of the ideals of constructivist theory due to students needing to assimilate old knowledge in a new environment with new understandings. It is a primarily student-centered task where students are creating their own understanding and procedure for moving the Sphero through the maze. Regrettably, the Sphero Maze activity does not promote a significant amount of creativity or inquiry learning. This can be easily overcome in future iterations of the activity. The WHO workflow can be utilised to analyse the pedagogy and assessment of digital technology usage. The workflow identified the usage of Sphero robots to enhance the learning of visual block coding and algorithm design. It also identified computational thinking skills should be used to think and engage with the activity. Students will be able to effectively collaborate by the completion of the activity in order to solve a problem. By using the activity theory, I was able to analyse the STEM education practice to recognise the influences and challenges associated with the teaching and learning of the Sphero Maze activity. Regarding the activity set of a teacher, the tools and signs that need to be considered include content knowledge of the new curriculum, functioning technology, whether it be Wi-Fi, charged robots or connectivity, and utilising a constructivist approach to the STEM learning practice. The rules that need to be considered are curriculum elements that are mandated to be covered and time constraints around delivery. The students, teachers, teacher aides, and the Deputy Principal of Technology all have a feasible stake in how the teaching of the activity occurs and its success. This is the community element. The division of labour was solely paired learning. This is due to the majority of the teaching having already taken place and the students now constructing their own knowledge between visual block coding they learn in Scratch to the coding of a Sphero. Regarding the activity set of the student, the tools and signs that need to be considered include using a collaborative learning process and connecting to prior knowledge. The rules that need to be considered are the student's ability to work in small groups, having a growth mindset, problem-solving skills, and ability to engage with computational thinking strategies. The community aspect only includes students and teacher aides. The teacher at this point doesn't have a lot of influence on the student's learning, as it's assimilating previously learnt knowledge in a novel situation. The division of labour facet involved paired learning, which is organised by the teacher, who pairs students due to their communication style rather than their friendships or intelligence. The main contradiction in the teacher activity set is between the subject and the tools and signs. The main contradiction in the student activity set is between the subject and the rules. The main reason for this is the digital technologies curriculum is only in its infancy, with its mandated implementation not beginning until 2020. Therefore, deep understanding of the curriculum and concepts by the teacher, as well as the mindset and thinking patterns for optimal student learning, hasn't matured in its development yet. There are three main digital fluencies that need to be improved or developed in according with the STEM education practice of the Sphere Maze activity. Creativity. There is only a finite amount of ways to solve the maze using a correct algorithm. Inquiry learning. There was no inquiry element to the activity. Students only had to work out a correct algorithm. It was purely problem solving. And mode switching. There was no mode switching between online to offline or plugged to unplugged. It is important that students learn how to correctly complete both versions of the activity. As previously mentioned, future iterations of the activity would provide an opportunity for improvement of digital fluencies. The Sphere Maze activity needs to provide students with the opportunity to think critically and creatively. Not only is this part of the Australian curriculum general capabilities, but it is a crucial 21st century skill. Providing an authentic context and problem requiring a diverse and novel solution will deeply engage students in inquiry learning. This could be initialized whilst maintaining the maze as a base element. Providing students with the opportunity to complete the maze as an unplugged activity would promote the flexible skill of mode switching. I am confident you can now make valid connections and understandings between the Sphere Maze activity and digital fluency.